right, so in the 2D world, when we're looking at, single variable functions, taking limits was not really that bad, right? I mean, a limit, like if you think about like what we're doing as we're looking at, like when we're evaluating limits, we're just saying, hey, at a certain point, at like let's say x equals a, what is my function f of x? As I get really, really close to a, what is my function approaching? So from the right, what value is my function approaching? And from the left, yeah, I got my lefts and rights correct. What value is my function approaching? And that wasn't like that crazy, right? We knew a limit didn't exist if you, for example, you had something like this. We knew that, hey, if from the left side, my limit wasn't approaching, or from the left side, my function approaches a different value than if it were from the right side, the limit doesn't exist. And the way we write that is say, the limit as x approaches a for f of x equals some value L, meaning there is a limit. It will equal some value L if the limit as you approach x from the right side equals the limit as you approach x from the left side. And that's what the negative and plus sign tells us. Negative being from the left, lower values, positive meaning from the right. Now, here's the thing about 3D, here's the thing about the 3D world is that now we're dealing with surfaces. We're not dealing with curves anymore. So I don't sure, let's just use this mug. Why not? So if I had this mug right here, and let's say this was a surface. Now, the equation for this surface, you could do x squared plus y squared equals some value, k, some constant like 9, and that would actually give you a cylinder. But the point being is, like, let's say you have, I guess this isn't really a multivariable function though. That's not a function. What's a good, I guess not a, sure, let's just do like, let's do, how do I do this? I guess maybe we could take all this stuff out. I don't want to do that. Okay, I'm just gonna, oh my god, okay, I'm making a mess. I'm just gonna use this, my camera case. I don't actually use for this. I just use my phone for this. But the point being, if, let's say there was some value, right? The way that the 3D world works is you have two inputs, right? Two independent variables, an x and a y, and the output is some z, like some sort of height. Now, if this was a point on my surface, my multivariable function, then there are, a lot of ways to get to this point, right? You could go, like this, you could go like this, you could go spiral yourself in. There's an infinite amount of ways to arrive at a point on a surface. So if I were to just draw this out, just to give you a better, visual of this, if this is my surface in 3D, and this is my point, well, there's a bunch of different ways to reach that point, right? So when you're taking the limit, right? If I'm taking the limit, like as my ordered pair x, y approaches some value a and b for f of x, y, when would the limit exist, right? When would that be the case? In the 2D world, we know that the only two ways to really approach the x equals a is from the left and right. That's just how the curve is like defined. There's no, you can't go from the top or this way. You can only go in the way that the curve is defined. But now we're working with a surface where there's many curves that lead to this point. So when you're taking the limit of a multivariable function, it'll only exist if all paths as your ordered pair, if this is like, my a and b value right here, a and b right here, if my ordered pair x, y, right, any point along this thing, as that approaches a and b, it is reaching the same value L with any path, whether you're going this way, whether you're going in like a spiral crazy path like so. That's what needs to be true in order for the limit to exist. Every path must be able to take you to the same value L and as you're taking the limit, right? So what we can do is, so let's take this example. Okay, let's just do an example. I'm gonna use a different marker because my markers are kind of dying. Let's take the example, the limit as xy approaches 0, 0 for x to the fourth. Is that what it is? X to the fourth? X to the fourth minus 4y squared over x squared plus 2y squared. So first thing you should always try to do when you're taking any limit is substitute in 0, 0, right? And what we get is that there you get 0 over 0, right? Indeterminate form, that just means a function isn't defined at the point 0, 0. Now, what in old Calc BC or Calc 1, Calc 2, what we would do is we would use L'Hopital's rule, right? Take the derivative on the top and the bottom, and we can't really do that, right? We're going to learn about partial derivatives tomorrow, but partial derivatives are a little bit different because it's more like how does your function change as you change a single variable, and it's like we have two variables here. Are we going to take partial x part? Point is, we can't really use L'Hopital's rule yet, if at all. But what we can do is examine, right, whether this limit exists or not by seeing is there any path. Well, we'll do all paths lead to the same limit, and if not, what path kind of leads to a different answer, right? And in that way, we can essentially prove that the limit doesn't exist because there's a path that won't lead to the same limit. So let's think about this. If we have our surface, let's say along the path x equals 0. So we're moving along the xy plane, and the first path is along x equals 0. Well, x equals 0 for every point along the y-axis. So this is really just moving along the y-axis. And if we're moving along the y-axis, that means x is always 0. So essentially what you get is the limit as y approaches 0, right? Because x is already 0. The limit as y approaches 0, and these x's become 0. So I get negative 4y squared over 2y squared. And this is not a terrible limit to evaluate, right? You can just cancel out the y squared, and you get negative 2. And if you were to graph this, you would get like a line, and there would be a hole at y. Well, if you were to graph this in terms of x, you would have a hole at x equals 0, and then, but it would the line would always be approaching negative 2. So that's not a terrible limit to evaluate. And then if we were to now let's take another path along the path of y equals 0, and that would be along the x-axis because every point along here y is equal to 0. So this is along the x-axis. And same thing, you're taking the limit as x approaches 0 because y is already 0, and you're getting x to the fourth minus 0, right? Because I'm just putting in 0 here because I know y is going to be 0 now in this limit. And I put a 0 here, and I get x squared. And this if I were to evaluate this is really just taking the limit as x approaches 0 for x squared. This is just equal to 0, right? You can also do L'Hopital's rule if you'd like. I wouldn't recommend it because it's kind of, you could, right? Because now we're working, what we've done is we've taken a 3D limit and separated it kind of into these 2D limits. So you can use L'Hopital's rule when we're working with just good old single variable functions, right? Like x to the fourth over x squared, or negative 4y squared over 2y squared. But regardless of how you evaluate your 2D limit, you see along the along the y-axis and the x-axis, you get different values. You get negative 2 and 0. So I know the limit does not exist. And what I want to show you real quick, let me open up 3D Desmos. Let me show you what this actually looks like, because it's pretty interesting. Let me go to 3D Desmos. And let me just loading right now. And let me put in x to the fourth minus 4y squared. divided by x squared plus 2y squared. Well, yeah, this is kind of crazy. So you get this really weird looking shape that kind of looks like this. And you can see if we were to go along the x-axis, right? Oh my God, wait, it's kind of hard to turn it. Oh my, excuse me? It's just gonna keep turning. Okay, there we go, that was kind of weird. But you can see as we go along the x-axis, it looks like the function is that's really annoying. It's gonna look like the function is approaching 0 as we're going along the x-axis. But as we're going along the y-axis, the function looks to be approaching -2. And I would encourage you to open up Desmos and get a better look yourself. But the idea is that there's the function is approaching two different values through two different paths, right? So the limit cannot exist, right? There's no set value that the function is approaching as an ordered pair x, y approaches 0, 0. So let me get my marker. Where'd it go? Oh, it's right here. Oh, where'd my marker go? Oh my God, I'm low-key a mess. Okay, so that is one example of a type of limit, right? Like where the limit wouldn't exist. And in all honesty, it's gonna be really easy to prove that limits actually do exist. It's harder to prove that limits do, like a 3D limit does exist. Did I say that right? Yeah. It's easy to prove that a limit doesn't exist because you just need to find a path where the resulting limit is different from everything else. It's harder to prove that a limit actually does exist. So let me just find another example I could work through. Okay, so let's say you want to take this limit. So we're going to do the limit as the ordered pair xy approaches 0, 0 for 6x squared times, or cubed, sorry, times y over 2x to the fourth plus y to the fourth. Okay, so let's think about this, right? We wanna either show that the limit, we wanna find the limit or show that it doesn't exist. And the two obvious paths right now. So the paths we can always check for, just off the bat. First of all, substitute in your ordered pair, right? You get 0 over 0, meaning the function isn't continuous there. So we have to, manually take the limit. And what you would find is that, okay, well, along the x-axis, so along the x-axis, that would be when y is equal to 0, right? So as when you're moving along that path, as you're taking the limit as x approaches 0, you're doing 6x cubed. This just becomes 0, right? Because you're just putting in a 0 there, over 2x to the fourth plus 0. Well, you have a 0 on top over some number, this limit will just evaluate to 0. If you're going along the y-axis, you're going to find, I'm not going to write this out, but along the y-axis, you get the same thing. Actually, I will write it out. As x approaches 0, you get the limit as y approaches 0 for 0, essentially, times y over 0 plus y to the fourth. Wait, never mind. Okay, yeah. You get 0 on top over y to the fourth. That limit just becomes 0. So now you're like, okay, well, hey, along the x-axis and the y-axis, the limits both end up equaling up. Does that mean the limit's equal to 0? Well, there's other paths, right? You can take any kind of path along the xy grid, right? I don't know what this surface really looks like, but I could go along the x-axis. I could go along the y-axis, and maybe there'd be a bump here, and I would have to go up. I could go along those axes, but I can also go in a path like this. I could go in a path like this. There's a bunch of different paths. That's a key idea. That is a core problem with limits in 3Ds, is that you have all these multiple paths that you can take. That's what makes them kind of tough to solve, but that's a key thing that kind of makes a lot of these limits not exist, is that there are paths where it doesn't wouldn't equal the same thing as these two paths, right? So key idea is that, well, what path could, not like cause it to or what path could have a different limit than 0? You can try the path y equals x, right? So along y equals x. So visually, that would look like going along this line right here, right? This is y equals x. And the reason I'm choosing y equals x is because what I can do now is I can say, well, all y's, I'm just going to set them equal to x. So I'm really taking the limit as x approaches 0 for 6x cubed times x, because now all the y values have become x as I travel along this path. They become the same number, over 2x to the 4th plus x to the 4th instead of y to the 4th, right? And I get 6x to the 4th over 3x to the 4th, which is going to equal 2. So that means, because I got a different, or whoops, my notation is really bad, sorry about that. I'm taking the limit as x approaches 0. That would end up equaling 2. Now, 2, that's a different result than these going along the x or y axis, so I know the limit does not exist. But why did I choose, how did I know to choose y equals x, right? There are infinite amount of paths. Couldn't I have done y equals x squared? Let's try that. Let's say we go along the parabola, which visually, remember, it would look something like this, right? It's like that parabola, y equals x squared. So if I were to take the limit as x approaches 0, 6x cubed times x squared over 2x to the 4th plus, we're doing x squared, wow, x squared to the 4th, so it would be x to the 8th. So I would get 6x to the 5th over 2x to the 4th plus, or I'm taking the limit. Whoops, I keep forgetting that. Limit as x approaches 0, x to the 8th. Shoot, that's just going to be nasty limit to do. I could do L'Hopital's rule. And I think with L'Hopital's rule, I would end up getting, what would I end up getting? Would it get unbounded? Would it be an unbounded limit? That's the thing. I don't even want to go about solving this, right? Because my goal is to either show that it does or does not exist. And y equals x is really good to show that the limit doesn't exist, because then I get the same degree on top and the bottom. I'm thinking, hey, I have an x cubed here and an x fourth here. I can raise y to be like, I can not raise it, but I can have it be the same as x, and then I get x to the 4th on top, x to the 4th on the bottom. And that will allow me to take a real quick limit and show that it doesn't exist. So that's the key. Always try to find a path where your top degree is equal to the bottom degree, just to make that limit real easy. I think this might be an unbounded limit, but I'm not sure. I don't even want to think about it too much, because I don't need to. I can choose a path that gives me top and bottom degrees being the same. We can do more. One thing I want to show you is also 3D limits. Or 4-dimensional limits, right? If you have a function that's in terms of 3 variables. So if we're let's take a look at this limit. So the limit, let's do this limit from the book. So the limit, oh boy, the limit as x, y, z approaches 0, 0, 0, for xy plus yz squared plus xz squared over, oh boy, x squared plus y squared plus z to the 4th, x squared plus y squared plus z to the 4th. Okay, now it's the same idea. There are multiple ways to get to this point 0, 0, even in the 4D space. Now, key idea is, well, same idea, like what paths can will lead to like what paths will lead to there being a different limit than a different path. That's how we can prove the limit doesn't exist. And what we will find is that, okay, let's say, first of all, plug it in, right? You get 0 over 0, so we're gonna have to take this limit just manually. And if I go, let's say I go along the x-axis, I would eventually, I'm not going to do this, you can think about this, right? Because going along the x-axis, that means y and z is equal to 0. Y and z equal to 0, right? And then I do the same thing along the y-axis, along the x-axis, or z-axis, or z, I don't know why I said z. And when I do this, going along one axis just means the other two variables would end up equaling 0. And you can see for the x-axis, if I make y and z equal to 0, there's a y and a z in each term, so the top would equal 0, the y's and z's here would equal 0. So my limit would end up equaling 0, and I get the same thing when I go along the y and the z axis. Now, what path could I take? I want the top and the bottom to have the same degree in order to take the limit lickety split. And I would, hopefully you kind of see, I have a z4th here, and I have a y squared x squared term here. Maybe I could get to z to the 4th, right? Usually you want to raise the smaller powers, right? I know z is the bigger, like it's always the bigger power here. It's either z to the 4th, z squared. So I can raise x and y to a larger power. And I can even say, hey, let's go along the path where x equals, or x is equal to z squared and y is equal to z squared. And when I do that, you can see I would have the limit as x, y, z. What is that? Is that a triple pair? Ordered triple pair, maybe? So x times y, well, it's z squared times z squared, that's z to the 4th. Y is z squared, so so z squared times z squared is z to the 4th. I have x to z squared, so z squared times z squared is z to the 4th, right? I'm just substituting in y and x for z squared, or substituting in x squared, or, oh my god, substituting in z squared for those two, and then all over z to the 4th plus z to the 4th, right? I'm squaring those. I get 3z to the 4th, and that limit would end up just equaling 1. So now I know this doesn't match. Oh, and I'm sorry, this is really the limit as z approaches 0. So now this doesn't match my other path, so I know the limit does not exist. So that's a general idea behind all of this. Now, one thing I want to touch on, it's continuity, right? So continuity is not a crazy idea, right? If you have a surface, if it's continuous, if at all points, you can take the limit, right? And you can, like, for example, if this was a continuous surface, there's no holes, asymptotes, nothing weird, like at this point, you can see that all the surrounding area, right, the surrounding area here, there's no discontinuities there. So I can just take the limit along any path, and the limit would just equal the value of that function. That's what makes it continuous. I think same definition for 2D, I believe. So why is that helpful? Well, for something like, well, first of all, polynomials are continuous and rational functions are continuous everywhere except where outside, everything outside the domain, right? So if I had something like let's say I had the limit, right? Like so, we're doing the limit as xy approaches 0, 0. And we're going to do the limit for let's see, 1 over 1 minus x squared minus y squared. Where is it going to be discontinuous? Well, it's going to be discontinuous. This is kind of a cool graph. It's going to be discontinuous along like a circle. There's actually like so like the graph would look something, it would look something like this, where you have this circle and then there's all these values up here. It's like a really cool asymptote. And the reason it's like a circle is because, well, when x, like the idea is that, well, x1 cannot equal x squared plus y squared. Or I guess 1 minus x squared minus y squared cannot equal 0. So 1 cannot equal x squared plus y squared. Well, that's going to be a set of points that form a circle. So along this circle is where it's discontinuous. But everywhere else, for example, 0, 0 right here, it's continuous because it's a rational function. So I can just substitute in 0, 0. I get the limits equal to 1. So that's one way you can find 3D limits, right? Using like just the continuity of the function. Here's another way, actually. Another pretty interesting way to find a limit is using, so let's say I'm doing this. Oh, I think, okay, yeah, the notes must have messed up. But let's say you were taking this limit. The limit as xy approaches 0, 0 of x squared plus y squared times ln x squared plus y squared. Now, if I were to substitute in 0 and 0, I would get 0 here times ln 0. ln 0 is negative infinity. So I get the form 0 times negative infinity. That is indeterminate. And one way I can go about solving this is actually thinking about polars. I know from polar definition that x is, the x coordinate in Cartesian is really just r times cosine theta in polar. Y is r sine theta. And I know that r squared is going to equal x squared plus y squared. So as x and y approaches 0, r would also approach 0, right? And if you think about, like, if as a point is moving towards the origin, that just means, in polar, that just means that r is approaching 0. But specifically, it's approaching 0 from the positive side. The idea being that because this is r squared, and to find r, you would have to take the square root. That would just end up being all positive numbers. So it's really r approaching from the positive side. But when we make these substitutions, I can say, well, this is the same thing as the limit as r approaches 0 from the positive side, r squared times ln r squared. And I can make this is still indeterminate, right? I have 0 times negative infinity, but I can make this into something I can do L'Hopital's with, r 0 plus, so then I can get ln r squared over 1 over r squared, right? I'm dividing by 1 over r squared, which doesn't change the expression, because when I divide by 1 over r squared, I'm multiplying by the reciprocal, and the reciprocal is r squared. So it's like the same expression, but now I can do L'Hopital's rule, because I know if I were to take the derivative, right? And on a math test, you would show like, oh, this approaches 0, this approaches infinity, this approaches infinity. L'Hopital's rule applies, but in this case, I'm just not gonna do that. I'm just gonna say, okay, the derivative of this is 2r. Well, I do derivative of the whole thing, so 1 over r squared times 2r. So I just get 2 over r. I'm just gonna put 2 over r on top. Over the derivative of this would end up being negative, so it's going to be r to the negative 2, right? That's what I'm taking the derivative of. So put the negative 2 in front, and then I get 1 over r to the negative third. So I get negative 2 over r to the third. So I can cancel out the 2's if I'd like, but I get the limit as r approaches 0 plus. 1 over r times its reciprocal negative r squared. This would end up just equaling 0. I would end up getting 0 from this limit. So polars are another way to go about finding limits. There's also the squeeze theorem. And I don't fully understand how you can use the squeeze theorem. Almost. I just don't understand the last part. In the school that the notes I've been using is from my high school. They don't cover squeeze theorem, and I don't know how the book doesn't really go into it either. So I'm not going to worry about it. The main thing is just being able to show that the limit doesn't exist, or using tricks, not tricks, but using like continuity, using factoring. Like there's some limits that you can just factor and it'll equal a real number, and using polar. So I'm gonna leave it at here. Hopefully this video is helpful in some way, and yeah, thank you for watching.